what is the mean age of air and how do I calculate it? So the mean age of air, and if you look up the definition from various papers, is basically defined as the average time for air to travel from a supply inlet to any location in a ventilated space. And it's a way of kind of characterizing the exchange rate of air or fluid of any type. They calculate this experimentally using what's called either using a tracer gas procedure where they have an enclosed space that has none of the tracer gas in there, and then they supply through, the supply area, they supply a tainted portion of gas and measure how that concentration inside that space changes at a particular location over time. And then they use some averaging to determine what the average time it took for that tracer gas to get to a particular location. Another method is a step down, and it's kind of the opposite of that, where you fill the room with a tracer gas and then you vent fresh air into the space and you watch the tracer gas disappear over time. So that's the averaging process that this is trying to represent. And so if you just think about, for instance, the step down procedure, the age of air at a particular location is simply the integration of the concentration at a particular location from some initial value out to infinity, basically until it's gone, and then you divide it by the initial concentration that you had there. That's the way you do it. And so I thought maybe we could just kind of go through some examples. It's like we could actually calculate that. And so I kind of picked a simple example here where we pick a velocity field kind of going from left to right, and we sample a gas value right here at these three locations. We'll source this area right here with a mass fraction of 0.5. And then we calculate this in a transient way and watch the value at each one of these points change. And then since fresh air is coming in on the left, what we would expect is that the concentration at this location would be a constant value and then begin to fall, and then it would disappear, and so on and so forth as you go down. And we can kind of calculate this value directly. So if we did that, we get curves that look like this. So here we have a concentration on 0.1 where it was 0.5 for a while, and then it starts to dissipate, and then it falls very rapidly, and then it tapers off. And you can see kind of this procedure, this evacuation process actually happens over 10 seconds. And so for this location, if we use that formula, we can actually calculate, if we do that integration of the area under that curve, we can come up with the mean age of air at that location to be 13 seconds, 13 and a half seconds. And then for location 2, it would be 26 and a half seconds, and location 3, it'd be 39 and a half seconds. So it's basically the integration, and you kind of gather the age of air by integrating the area under the curve and use that, and that's the metric for the averaging process, and that represents the average time at that location. So, but that's kind of a lot of work, and we don't want to run a transient simulation. So can you calculate this mean age of air everywhere in the domain with a steady state solution? Can we do that? Well, steady state solutions, they've already kind of characterized the convective and diffusive behavior throughout the whole flow field. So we should be able to do this without actually calculating a mass fraction field and look at it and get an integrated value directly at every single location in the domain, and then we can essentially have a field of time. To do this, this can be done by adding a scalar field to your solution. And in Azor's sense, it would be a mass fraction field. And what we do is then we set a mass fraction source term in each cell equal to the density of the fluid in that cell. And in these cases, the density is constant, so it's just a constant number. And then the inlet boundary conditions for our scalar boundary conditions are 0. And we run a simulation. And we get a field that represents the mean age of air. So if we go back to that sample problem that I chose, we can actually calculate this again. And here we've done this with a steady state solution. And since it's very satisfying here, if you look at the difference between these two calculations, either the steady state or the unsteady, the number is essentially identical out to 3 decimal places for each location. So it's basically the same exact value, only you get the solution with, using a steady state approximation. I'm going to pick another example here, and this is a swirl chamber. It's 2D, and we have a slot at the top where air is going to come in. It's turbulent flow, and then it essentially will go around and come out here, and you'll get this kind of tumbling flow here. And I thought maybe this would be a little bit more interesting problem where we might want to look at. And I think this problem is a good representation of an HVAC system physics. Because in this case, you have regions that are kind of dominated by convection, where you would maybe have supplies and return registers, like in any room where you have an HVAC system, you have supplies where you have, a strong jet of air coming in, and then registers where maybe you would have a little bit higher flow where the air is leaving, but generally inside the space, the flow is really low. So you really have a lot of regions in a space, in a room or something, that are really not dominated by the flow. They're really dominated by turbulent diffusion more than anything else. So I thought this would be a good problem to look at, because this problem, it has to balance between kind of characterizing the flows which are convection dominated and also characterizing the flows that have secondary flows, a turbulent diffusion, where that is the dominant force, and the velocity is, the velocity patterns play a very small role in how a gas travels in that room. In this particular problem, the red area kind of represents the convection zone, where the flow is just kind of going around and out. And I've chosen 3 sampling points here. I've labeled them C1, C2, and C3. And these are kind of the convection areas that are dominated by convection. So you would expect this location to kind of evacuate first, second, third. And then we have this blue area, which is really dominated by turbulent diffusion, because the only way that any tracer gas in this location is going to get out is if it travels perpendicular to the velocity pattern to get out. And so I've picked a couple of sample points here. I've labeled them D1, D2, D3, D4, and D5 here to kind of characterize the diffusion portion of this problem. And I thought, okay, let's look at that and do kind of the same thing. And so I ran an unsteady simulation of this. So we'll start and we'll run it for a while, and you can kind of see how this space gets washed out. So after about 4 seconds, you see I stopped it. Most of the perimeter has already been evacuated. So the convection dominated portion of the problem is essentially complete. But now we need to work on the diffusion problem. And so you can kind of see the diffusion process is now taking place. And here the problem is really not the velocity field, it's the turbulent diffusion that's been calculated in this problem. And this is going to go on for a while. It takes a while to pull all of these tracer gases out of this area and to exchange it, and it just goes on and on. I think you get the idea. So in the transient analysis, if we look at those points, we can kind of see what's happening. So the first 3 points, they happen very rapidly, and so the area under those curves are quite small. And so they go down very rapidly, and then there's a taper off. But the diffusion points, it takes a while for them to trace out, and it goes all the way up to 300 seconds is how long I ran this in order to get these values. So some of the time to evacuate this chamber, you know, sometimes are on the order of 1 second, and some of them are on the order of 56 seconds on average. But some of these 56-second values, actually there was gas, there were, you know, the tracer gas kind of extended all the way up to 250 seconds, but it's just a very trace amount. And so the averaging process ends up with, you know, numbers of this sort. If you do a handbook calculation of this, where you take the volume of this and divide it by the flow volume coming in, you would come up with a mean age of air on the order of 8.9 seconds. So, and which is pretty close to this 6-second mark right here. Now, if we do this same thing and we run our steady state analysis, we get these 3 points again. The outlet is always going to be the same value. If we do a mass weighted average on the outlet, we're going to get the average time. But once again, you can see that these numbers out to 2 decimal places match very well between the steady state analysis and the transient analysis. And the transient analysis was, it ran for 300 seconds. It's about 60,000 time steps. So there's a lot of calculations involved in order to get there, and it still buttons up pretty nicely. And this was only run with a floating point. I suspect that we would even get higher correlation here if we ran this in double precision. So this method of calculating the mean age of air in the steady state really does do a nice job of characterizing kind of an unsteady behavior using a steady state analysis. I thought maybe it would be good to kind of say, well, what happens if we wanted to look at some statistics here and compare one simulation to another? What would be some of the values that we might want to look at, and what would we see? And so what I chose to do was run the same simulation, and all I did was change the inlet turbulent intensity. And the one that we looked at initially was run with an inlet turbulent intensity of 20%. And I changed it to 5%. And I said, okay, what do we see here? And it really comes down to some, I guess I wouldn't say inherently obvious values. So like in the middle here, when you cut down the turbulence, you see that the time in the middle goes up, which makes sense because it takes longer for the gases to move out of here if you have less turbulent diffusion. But on the flip side, if you look right here, the average age of air actually goes in the opposite direction, where it's higher when you have more turbulence and lower when you have less turbulence. We can also look at the volume average value as a way of kind of characterizing the overall simulation. And this is where you would essentially take the age of air time in every single cell, multiply it by the volume, sum that up, and then divide by the total volume. And you kind of see kind of a characterization here where you have 32 seconds for a volume weighted average and 38 seconds. And you would expect the one with a lower or smaller turbulent intensity to take longer. But this number right here, both of these are significantly larger than the original value, which was right around 8 seconds. If you were to just use a handbook calculation to come up with what the exchange rate should be in this. What we can do now that we have all of these times, and in a large, complicated 3D problem, how do we kind of convey this type of information to our customer? This is an animation of a classroom, and this is the age of air in the classroom, and you can kind of see right over here, this is where the air registers are bringing fresh air into the room. And what we've done is taken a steady state representation of this and kind of walk through. This is all done post-processing wise, and create iso surfaces that kind of march through your time, march through in time. And so we can kind of get a visual that gives you kind of a representation of how the air in this room gets evacuated. And right down here it's showing time. So the air comes up, it smashes on the wall, on the ceiling, and then it begins evacuating and clearing out the space. So this is a good way of showing visually what is happening, and it gives a very transient depiction of what's going on in the room, and how, like at this point right here, if we stop it, we say, okay, right here, it takes longer than 7 minutes to evacuate this inside portion of the room, whereas these areas over here, it takes less than 7 minutes. So the mean age of air, it's really a method for characterizing the mean time to exchange a fluid at a particular location in an enclosed space. It really allows you to kind of characterize a specific location and how long it takes to get rid of a tracer gas there. It can be done in steady state, and it can also be calculated as a post-processing process. So we can, you can run your simulation, and then once you think you have everything you want about it, you can go back and calculate the age of air, or you can calculate it as you're doing your steady state calculations.